you might have a central domain controller, and you would also probably have not only cameras in the system, you also might have a couple of ultrasonic sensors or radar sensors, whatever you name. Assuming you would like to implement something like this in a device, we would recommend the next generation of our products, which was called Sync-UltraScale SoC. It has a similar setup, and I won't go through the details on this slide. It has a similar setup. It has a processor subsystem, which in that case doesn't have only a ARM-A9 dual-core processor, but a A53 quad-core processor, plus a few other processing entities. And it still would have a big part of programmable logic, where you could implement still a lot of the functions that would be required for such a system. And as you might remember here in the slide, so part of the design for sensor pre-processing and object tracking might be implemented in programmable logic, in the yellow part. The sensor fusion, stitching, and object classification would be running on the A53 cores, which would be behind this block here. And still, for some really safety critical actions, you would have dual R5 cores inside the device, which also could be run in lockstep mode to give you, all required safety functions. So, this would be a more detailed block diagram of the device I was just talking about. Application processing unit with quad-core A53s, a small GPUs, a few standard peripherals, memory controllers, dual R5 cores for safety critical functions, a couple of additional system functions for security and functional safety needs, standard peripherals, and a piece of programmable logic. As I mentioned earlier, functional safety is a key point. So this is just supposed to outline that we took quite a few measures on this device to make sure that it's capable to fulfill functional safety requirements. And without going into all the details, just a few key highlights here. We have ECC on all critical memories, also on the PL part. We have the A5s, which are supposed to be able to support ACC in your system. It can be lockstepped. And one question that we usually get when we're talking about FPGAs in safety critical systems is the programmable logic part, which is a SRAM-based technology where a bit flip or a single event upset could occur during the operation of the system. Therefore, we're also offering a so-called SEM-IP, which is an acronym for single event upset mitigation. So this IP block will constantly monitor the configuration of your device, and in case there is a single event upset or a bit flipping, it would flag a signal, which would allow them to either take the according measures or reconfigure the device or whatever you think is necessary to make sure that nothing is happening. So this is just the product table of that device family. The important thing is the device comes in different sizes, where the processing system is identical in all devices. The only difference is the programmable logic part, where we have a different number of logic cells and memory included. But it's important to note that we always provide pinout compatible versions. So assuming you decide to go for the smallest package and build your board, you can either put a CU3 EG or a CU2 EG on your board, whatever you require. So usually our customers use this capability to build a scalable platform, meaning that they build one system, one PCB, and then depending on whether it's the mid-range or the high-end system, they would either go for the bigger or the smaller device. I mentioned earlier that we have a partner company here at the booth outside. So Xilinx is a company out of Croatia. They have been assigned to Xilinx for almost since the beginning. They are focused especially on camera-based solutions. What they are offering, and which we usually recommend to our customers, is a so-called Logi ADAC, Logi Advanced Driver Assistance Kit. It consists of a demo board, an an adapter, different number of cameras, can be 4, 5, or even 6 if you require it. Some licensed IP and some tooling. And this pretty much gives you a off-the-shelf ready reference design that you could run in your lab or even put into a prototyping car. And it comes with a few standard software applications, 3D surround view, rear view camera, blind spot detection, and of the other things, face detection, driver drowsiness. This is actually a demo we have outside at our booth, and it's definitely worth checking this one. One other thing they're offering is a so-called logic recorder, which is pretty much a data logger for the camera data that you collect while driving around, or whatever you do in your lab to collect data. And then you could use that data with the Logic SDK tool to train your algorithm to detect whatever you wanted to detect, maybe pedestrians, cyclists, cars, whatever. That will usually have to deal with two implementations. One would be localization and mission planning. There are a couple of different algorithms that would be required for this, which usually require a lot of performance and also require the corresponding ASIL rating. So depending on how you would, or what specific solution you would be looking at, there's different architectures we would recommend. So we do not believe that our device is the only solution and you would require nothing else. Depending on what you would like to do in your system, a standard sync device or a more complex sync ultra-scale plus device could be the center of the system. But depending on how much performance you would actually need and what interfaces you need and what else is required, it could also make sense to have different devices on board, or also add a supplemental microcontroller. So we usually we have a couple of very skilled system architects within Xilinx. So whenever you would start the system, we would recommend to get in touch so we can help you guide to the right solution. Not necessarily meaning that we would be the only device, but maybe trying to find the optimal solution. CNNs, machine learning. This actually is a topic that we hear at every customer meeting since the last couple of months. The good thing for us is we've been looking into CNNs, and it's basically a lot of multiplication going on, which very well suits our FPGA technology or the programmable logic part in our SoCs. So we're already in close cooperation with a couple of OEMs. The interesting part there is that it basically consists of two parts. One, you need to decide for a specific network, AlexNet, GoogleNet, whatever. But no one in the industry yet has found out which would be the right network to use for a automated driving or ADAS application. So we're currently evaluating different networks. We have some first results, comparing also to other semiconductor suppliers, which pretty much determines for us that we're on the right track and that FPGA architecture is very well suited. The second part of a CNN solution obviously is the tooling that is required. The device alone probably won't do the job. You need the right tool set to be able to really make use of a CNN. So therefore we're also, we're not doing everything on our own. So we're about to provide a toolset which we call SDML, which is the acronym for Software Defined Machine Learning, which will bridge the gap between publicly available frameworks like Cafe or TensorFlow and enable you to implement whatever network you have developed with those tools into our device technology. So in more detail, we would assume the customer, our customer, would determine a reference network. We're using some of the standard just named open source tools for CNN network design. We would provide a model compiler which will help you to transform your model into an FPGA or a C design. For that, we would also provide the libraries either directly or to one of our partners. And then obviously we will have to provide a device compiler
transforming that into the bitstream for our devices. So I'm not going into details through this. So of course we provide the necessary processing elements in our devices. These are specified DSP blocks. ME is a new thing that we will launch in the next generation of our devices, which will be specifically tailored for CNN applications. And then obviously the devices and the standard development platforms, like the one I showed you through our partner. But CNNs do not, solve all the problems for autonomous driving. Another thing that we think is important is this application called Occupancy grid map. This is pretty much part of the localization process, trying to find out where is the free space in the environment, what are the options where I can go to with my car. Usually, in most cases, coming from things like a LiDAR sensor. And we've already done our homework, hopefully, and tried to find out how difficult it would be to implement an occupancy grid map in one of our devices. So you've seen here on one of our system architects did some deep dive and did some evaluation of what would be required. There's another nice feature that we could use called partial configuration, where we would actually try, during full operation of the device, trying to reconfigure parts or blocks of the design to make better use of the silicon. So our first estimation that for such an occupancy grid map, we would need maybe 60% of a CU5, which is you'll find in the former slides in the product table to get an understanding of how good that the